to everybody and welcome to Acadec's YouTube channel. Today in this video I'm going to solve a problem on electrostatics. To be more precise, electric potential. I read the question. Consider a point charge, positive Q, placed at the origin and another point charge, negative 2Q, placed at a distance 9 meters from the origin. 9 meters from the point charge positive Q. Determine the point between the two charges at which the electric potential is 0. Alright, so we have 2 point charges, positive Q and negative 2Q, and we are required to find the position in between the two charges where the electric potential is 0. So if I want to represent the charges, I'll have something like this. I'll have a certain charge, positive Q, and it's placed at the origin, and the coordinate of the origin is 0, 0. Now, I have a second charge, negative 2Q. The second charge, negative 2Q, that is placed at a distance of 9 meters from the first charge, which was initially placed at the origin. Now, the position where the electric potential will be 0 will be found in between the two charges at a certain distance. At a certain distance, we call the distance Z. It's going to be at a certain distance. At a certain distance, say Z, and Z is what we are looking for. At a certain distance, at a certain point, the electric potential will be 0. At a certain point between the two charges. So now, we need to use the formula for electric potential, which we know as V. Electric potential is KQ on R. Where K is a constant given by 9 times 10 to the power of 9 Newton meter squared per Coulomb squared. In this, then we are going to apply this formula to see what it's going to give us. We are going to find the position in between the two charges where the electric potential will be 0. It means we need to find the position in between the two charges where the electric potential due to both charges will cancel out each other. So, alright, we are going to first of all find V1. It means V1 is equal to KQ on R1. Let's call this equation 1. Then V2, consider the second charge, is going to be negative 2 KQ on R2. We call it equation 2. So for the electric potential due to the first and the second charge to cancel out each other, it means that V1 plus V2 should give us 0. Alright. V1 plus V2 should give us 0. And it means equation 1 plus equation 2 should be equal to 0. And this then means that KQ on R1 minus 2KQ on R2 to be equal to 0. And here we're going to now have that KQ R2 minus 2KQ R1, all this on R1 R2 equal to 0. And now, if 0, it simply means that the numerator is equal to 0, which is KQ R2 minus 2KQ R1 should be equal to 0. We can simplify by KQ, and we are going to have, we will simplify by KQ. For instance, KQ R2 will be equal to 2KQ R1. We can simplify by KQ, and we have R2 equal to 2R1. Alright, and R2 is D from our diagram. Will be equal to 2 into, but R1 now is going to be this distance. If this is the distance D, it means this distance will be 9 minus D. So 2 into 9 minus D. Now D will be equal to 18 minus 2D. We have 3D as 18, and D will be 6 meters. So the distance or the position in between the two charges where the electric potential will be 0 will be 6 meters from the origin. D here will be 6 meters. Welcome back. We are going to continue with the solution to Exo 2. I read the question. A positively charged particle is placed 35 millimeters from the center of a sphere with charge 311 microcoulombs and radius 20 millimeters. If the particle is repelled by 19 millimeters, what change in potential does the particle experience? So now we are going to calculate the change in potential that the particle experiences. The charge was given to us as 311 microcoulombs. The charge here, 311 times 10 to the negative 6 coulombs. And then we know that the electric potential is given by the formula V equals to KQ on, so the formula here, V is KQ on R. Okay, so now the particle was first placed at the position of 35 millimeters, and then secondly was now repelled by 19 millimeters. So we are going to have R1 as 35 millimeters, which is the same as 0.35 meters, and R2 as 19 millimeters, which is the same as 0.19 meters. Okay, so now to calculate the change in potential, in electric potential, we need to first of all calculate the initial electric potential and the final electric potential, and then we take the difference. So for the initial electric potential, we are going to have the initial electric potential, which will be equal to KQ, the same charge on R1. Alright, so if this is going to be equal to, means V1 is equal to K. We know that K is numerically equal to 9 times 10 to the power of 9 Newton meter squared per coulomb squared times the charge 311 times 10 to the negative 6 coulombs. All this divided by R1, which is 0.35, and then 0.35 in meters. Okay. And when we do this, we have the electric potential as 8.4 times 10 to the 6. Then now we are going to calculate the final electric potential. Now the final electric potential is going to be given by Vf P1 on R2 with this Ri Rf. Alright, Rf for instance. Alright, so I'm going to have the final electric potential as 9 times 10 to the 9 times Q 311 times 10 to the negative 6, then divided by 0.19 meters. And we're going to have the final electric potential as 1.5 times 10 to the 6 volt. Then now the change in electric potential. The change in electric potential is going to be equal to Vf minus V initial, and therefore it's going to be equal to 1.5 times 10 to the negative 6 minus 8.4 times 10 to the power of 6. This is 6, not negative 6. Okay, so it is going to be changed in potential. It's going to give us negative 6.9. Negative 6.9 times 10 to the power 6 volt. Change in electric potential. Alright, so this brings us to the end of the solution to Exo 2.